Welcome back. Last time we began to study machine learning in theory as well as in practice. And when we got to deploying machine learning models in practice, we studied the Titanic dataset, trying to predict from information about Titanic passengers whether or not they survived. Now, we saw that a very simple decision tree with very interpretable kinds of decision rules was able to model the data with almost 80% accuracy. So that sounds very impressive. However, we shouldn't take this result at face value. And the reason why is a phenomenon that I've been hinting at a few times now called overfitting. And the big message of overfitting is that you shouldn't take for granted that your data's score on the, or that your model's score on the data that you train it on will be similar to the score it will achieve when predicting new data. So predicting data that you haven't seen before is different from modeling the same data that you used to train your model. So let's go ahead and take a look at this in the context of regression. We're going to look at a really radical example where a model that achieves excellent score, or equivalently a very small loss function, a model that really fits the data well, is terrible at predicting unseen data. So let's give this a try. So first, as usual these days, I'm going to need NumPy, and I am going to need matplotlib, or pyplot as plt. There we go. Okay, so the first thing I'm going to do is just generate some very simple fake data. So I'm going to set my random seed to 1, 2, 3, 4. What this will do is, if you want to run this code on your own, setting the random seed will reset the random number generator to a specific state, ensuring that you can generate exactly the same random data that I do. And I'll generate x equals np.random.rand. So this is just 10 random points between 0 and 1. That's x. And then y is the log of x. And then I don't want exactly the log of x. I'm just going to add some random noise. So np.random.randn. This is bell curve shaped noise with the same length as x. So, oh, and I need to capitalize my x. There we go. Oh, no. np.random.random. There we go. Okay, so next, let's just take a look at what we have. So I'll make a figure, very simple, nothing fancy, and I'll scatter x and y. And okay, so this is roughly what I expected. I see that y on the vertical axis is larger when x is larger on the horizontal axis. There's a correlation, but if you squint, you might notice, hey, this doesn't look like exactly a straight line because we didn't use a straight line model. The true relationship is actually logarithmic. So this is our data for today, very simple. The models that we're going to look at today as examples are called polynomial regression models. And polynomial regression models are very simple in a way. They're the simplest version of what we sometimes call curve fitting, in which what we want to do is fit a curve through some data points. Polynomials are the simplest curves, and so they're great choices for curve fitting because they're very easy to work with. However, no one does polynomial regression, and the reason no one does polynomial regression anymore is exactly the problems that I'm going to show you today. So it's not important for you to understand the details of this pipeline that I've created here. So this is some code for implementing polynomial regression. You are not responsible for knowing how this code works, both because it involves some tools that we haven't really talked about and will not talk about, like make pipeline, but also because I don't want you to do polynomial regression. It's a bad idea, but it's very helpful for demonstrating the problems of overfitting. So we're going to do that today. So here is our function that will do polynomial regression for us. Now, our function has a slight sort of syntactic requirement here. It actually operates on two-dimensional arrays. So here's x, our input data, our predictor data. X is a one-dimensional array, and we can promote x to a two-dimensional array like this. So I just colon comma none creates another axis for x. So now x is a multi-dimensional array. And we can just check now that x has shape 10 and 1. So 10 entries in the first axis, 1 entry in the second axis. So this is the way that we need to supply x to our model. But now we're ready to go. So model 1 equals polynomial regression. For model 1, I'm going to use first order polynomial regression. And if you remember what a first order polynomial is, it's just a line. So polynomial regression 1, first order polynomial regression, is actually just a linear regression. So we've actually seen this before. So we're going to fit x, I need to promote x to the right shape. And we're going to fit x and y. So that's our first model. Now for our second model, which I'll call model 2, we're going to do the same polynomial regression, but instead of just 1 degree, we're going to do 10th order polynomial regression. So we're going to fit a 10th degree polynomial through our data points. So we're going to fit x and none y. Now, if you remember from your algebra classes, if you have a 10th degree polynomial, it can really get very wiggly, okay? The more degrees you have in your polynomial, the more opportunities there are for it to wiggle around. And a 10th degree polynomial can really wiggle quite a lot. So this 10th degree polynomial is more complex. It has more flexibility. It's more able to fit the data well. So let's see how that looks, actually. Before we sort of draw the picture, let's look at the scores. So I'm going to do model 1.score to see how we did on predicting on the training data, if you will, so the data that we use to train the models. And I'll compare that to model 2, same score. There we go. So this is kind of interesting. Remember that the score function for linear regression, if you haven't seen it before, the score function here, 1 is the best you can possibly do, but then you can also get negative values if you're doing very badly. So this score function comparison is telling us that model 1 did a pretty good job. So the score is 95% to 0.95. That's a nice score for linear regression, pretty good. But model 2, model 2 got 1.0, the highest you can possibly get in your score function. Now, how did it get this perfect score, model 2? Let's visualize this. So I'm going to just draw a set of x values that we'll use for plotting purposes. This isn't part of our machine learning pipeline. This is just some evenly spaced points for plotting. So I'm going to, when I do xfit here, this is 1,000 evenly spaced points between 0.01 and 1. So I'll do x.plot, xfit, and model1.predict xfit, color equals black. So what am I plotting here? When I do this, this is the, there we go. So when I add that line, that's the first order polynomial regression line. As we know, that's actually linear regression. And so when I do this, I'm just plotting the linear regression line against my data. So nice and simple so far. The next thing I'm going to do is add model 2. Okay, so let's add model 2. So I'm going to do xfit, model2.predict, xfit, color equals fire brick. Okay, so that'll draw it in this nice red color. Let's take a look. Well, okay, well that looks terrible and confusing. So I can't even really see what's going on my plot anymore. A good way to fix this is to notice that what's happening is that the y-axis has gotten blown up somehow. So we can just set the limits. So x.set ylim equals, I'm just going to set the limits equal to the limits of the data. So remember that y has a minimum and a maximum value. Y is just an array. And I'll add a little bit of padding. So my vertical axis is going to correspond quite closely to the extents of my data. So let's give that a try. Okay, that looks a lot better. So notice what's happened here is that model 2 in red has used its great flexibility and its ability to wiggle around in order to perfectly fit the data, right? So we see that model 2 perfectly passes through each of the data points in my data set. Now, this is attractive, right? Like we perfectly matched all of the data points, perfect prediction, no error. Machine learning is easy and we're done. Great. Now, of course, the picture is more complicated than that. And there's a reason that machine learning is not called curve fitting. These wiggles that you see, the big up and down oscillations in the Model 2, those are actually a big problem. And what are they a big problem for? They're a big problem for prediction. So let's take a look at prediction. So what we're going to do is predict some unseen data. We've seen that Model 2 performs perfectly on the data that we allow it to be fit to, sometimes called the training data. But we actually want to predict unseen data. This is the extra wrinkle that we haven't really talked about too much so far. But this is actually very fundamental. We want our models to perform well on data that they have not seen yet, because the model can memorize the data, no problem. If all you wanted was a model to memorize the data, you wouldn't need any machine learning. You'd just need a hard drive that you would store the data on. A model that actually distills the signal in the data and uses that to accurately predict new data is what we want here. So we're about to see that difference in action. So we're going to create the same data that we had above, just a new random realization. So x new is np.random.rand 10. So this is 10 new random data points. And then y new is np.log of x new plus, again, some bell curve distributed random noise. Okay, so now we have some new data. Our models have already been trained. We don't have to train or fit them again. So let's go ahead and actually check model1.score. So I'm going to evaluate it on x new. And I need to expand x new again and y new. And let's compare that to Model 2's score on the same data. Okay, so this time something kind of shocking has occurred. So Model 1's score has gone down. Okay, Model 1 had scored around 95%, and now Model 1's score has dropped. It's about 80%, 81%. So there's a significant drop, but the fact that Model 1's score is above 0 in this case indicates that Model 1 is still predicting something about the data, at least to an extent. On the other hand, Model 2's score has become negative 70,000. Now, what does that mean? To contextualize that, this score function is something called the coefficient of variation. And we're not going to talk about the mathematics of the coefficient of variation. What I want you to know about the coefficient of variation is that a flat, useless model that just guesses the same number for each prediction task, you say maybe it's a model that always returns the value 0, for example. That's a model. It's a very boring model, but it's a model. That boring model would achieve a coefficient of variation of 0. Okay? So the very flat, boring model that doesn't even look at the data and just says 0, 0, 0, 0, 0, that model is better than Model 2 at predicting unseen data. Model 2 is worse than useless. Okay? Let's take a visual look at this. I'm going to just keep using the same plot from before, and I'm just going to add some new data points. So I'm just going to add x new and y new, and I'm going to plot them in orange, and then let's show the figure. So we can see that what's going on here is that although Model 2 perfectly fits all of the original data points shown in blue, it's badly off, really badly off, on the new data points shown in orange. So it's off, for example, in some of these orange points, it's off by 2 or more. It can be off, I think, in some of these by even 10 or 20. It performs very, very badly for these new data points. Whereas Model 1, it didn't perfectly capture the original data points. It was close, and now kind of the same thing is going on. It's still pretty close to the new data. even though it didn't perfectly model the original training data. So there's a pattern here. The model, the data that we train our model on or fit our model on is often called the training data. Unseen data that we sort of test the model by predicting the unseen data is called test data. So we have training data and test data. Overfitting refers to the phenomenon in which your machine learning model gets distracted by your training data, in that it tries to fit the training data so well that it begins to fit the random noise in the data rather than the true inherent signal that will allow it to predict. It's like someone memorizing this like really long list of serendipitous facts without really understanding the real picture that makes all the facts hold together and makes them all relevant. What we want are models that do not have this issue, models that see the big picture in the data and don't get distracted by the random little noise pieces. This phenomenon, broadly construed, is called overfitting. You have an overfit model if your model is distracted by noise in the data and doesn't pick up the signal. And a characteristic signature of overfitting is performing much, much better in score on your training data than on your unseen test data. Overfit models do badly on prediction, whereas models that avoid overfitting can often do much better. I want to point out here that overfitting is closely connected to this idea of model flexibility. Okay, so this wiggly red line that we have was a 10th degree polynomial, lots of flexibility, lots of parameters to change. You can move the curve around in different ways. Very complex model in this way, able to fit many, many different kinds of patterns. But it's actually too flexible in that way. It was so flexible that it was able to get distracted. Whereas model number one was arguably not flexible enough, but it was also able to avoid being distracted by the fluctuations in the data. So models that are very flexible can be beneficial because data comes in many shapes and sizes, and you might want to be able to represent it in many different ways. But models that are too flexible also run the risk of overfitting. In the next lecture, we'll see the interplay between model flexibility and overfitting in a real-world context, and we'll begin to look at ways in which we can ameliorate and fix the problem of overfitting.